Hey everyone, I wanted to talk a bit about calculus. So you've been hearing me talk about calculus and how we're going to talk about calculus more. Now that time has come and your homework is finally going to include calculus. So let's just talk about some of the important concepts. So let's say that you have some function f of x, which I've chosen here. F is 8 plus 8x minus 3x to the third. So here's a plot of f of x versus x. And we've talked about derivatives before, right? The derivative, df dx, of this would be, because of the power rule says that a x to the n, say, plus b x to the m. If you take the derivative of that, dx of this is going to be a times n x to the n minus 1 plus b times m x to the m minus 1, right? So that's the derivative of this function. So if you take the derivative here, right, the derivative of this, of 8 there is going to be 0, right? The derivative of 8x then will just be 8, because x to the first power the power drops down by 1, so that would go away. And minus 3x to the third, the derivative of that is going to be minus 3 times 3x squared, or in other words, 9 minus 9x squared. So the derivative of this function is then 8 minus 9x squared. Here's a plot of the derivative versus time. You can see the derivative is always negative, or starts out positive here, but then it gets negative as you get to about this point here, right, where it reaches its peak. The derivative is negative because it starts going down, but it starts out positive at the beginning here. Okay, so that's differentiation, and that's going to be important, especially if you have, say, some position as a function of time, and you want to get the velocity, because the velocity is the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time. So this is something we've talked about. And then last week, I just barely started talking about indefinite integrals. And indefinite integrals, I started talking about integrals in general. So let's talk a little bit more about integrals. So you might remember that there was two things that I had said about integrals. One is that they are antiderivatives, and the other is that they are the area underneath a curve. So let's talk a bit about why it would make sense that the area and the antiderivative would be the same thing. So let's say that you have some function, little f of x, and it's this function here, right? It's this curve, and you want to find the area underneath that curve. And so you're going to call the area underneath that curve in this interval starting from some constant value a up to some variable x to be this capital F of x. So capital F is the area under the graph of a little f in this particular interval. Now, notice, okay, if I have here this region filled, this region right here is f of x, because this is the point x here, and I go ahead a little step further, x plus delta x, then call this whole function, this whole region here, f of x. This would be capital F of x plus delta x. Then I could take the difference between those two, right, the difference between f of x and f of x plus delta x, it's just going to be this little region right here, right, which had the lines, the squiggly lines going this way, but not the squiggly lines going that way. Right, so if I take the difference between the two, what I'll get is the area of just this little region here. And so the area of the graph in that interval between x and x plus delta x would be this difference here. Okay, the area of this little rectangle with a height f of z, where z is some value between x and x plus delta x, so that you can find a rectangle here at some point z between these two values, where you can say, okay, the area of this rectangle is the same as this area underneath this curve. That should be a pretty easy proposition to buy. So the area then of that rectangle is going to be f of z, wherever this value is between x and x plus delta x, times this delta x, the width of the rectangle, right? So this quantity here is going to be equal to then f of z for some z between x and x plus delta x times that width delta x there. Now, if I divide both sides of this equation then by delta x, and that would look like this, I can then just take the limit as delta x goes to 0, and you'll see that then I have the limit as delta x goes to 0 on the left-hand side. This is just the formal definition of a derivative right here, right? And since z was between x and x plus delta x, if I take the limit as delta x goes to 0, this on the right-hand side here is just f of x, right? And this here, this is the formal definition of a limit of capital F of x. Sorry, the formal definition of a derivative, right? So what I have then is that the derivative of this function that I started out talking about is equal to the original f, which we were trying to find the area underneath its curve. So that's why the two concepts are so closely related. The area under the curve is related to this antiderivative property because of this derivation that I just went through. Okay, so sometimes we use primes to denote derivatives. So this is telling me that the derivative of that area function is equal to the original function itself. So we can then flip this thing around and say, we can get, let's define some operator. We'll give it this symbol that takes us in the opposite direction. That undoes the derivative, the antiderivative function. So if I applied that to both sides, it would look like this. Right. The integral, so capital F, the antiderivative, is this integral of this function over x. This integral sign here it looks like an elongated S. It's a kind of a sum over these little intervals dx as you walk along. So earlier we talked about the area underneath curves always in terms of doing it numerically or doing it just by finding the area of triangular or rectangular trapezoidal regions underneath something. This works for a continuous smooth curve, and the integral comes with certain rules, and you do not need to memorize these rules because I'm going to give you a handout. It is already located on Canvas under, I think it's General Resources, it's called. But I'll give you a table of common derivatives and integrals. You can use it on your test. You can use it on your homework. It should be helpful for you. It starts out on one page with some standard things about derivatives, which you're probably, some of which you're probably familiar with already. Things like if you take the derivative of f of x plus or minus g of x, right, you get the derivative of f of x plus or minus the derivative of g of x, and the all-important power rule, things like that. That a constant multiple, the constant multiple rule, that the derivative of a constant is 0. Okay, so those are the derivative rules on the one side. On the other side, you get the integral properties. Okay, many of them are very similar, right? That the integral of some constant times a function is just that constant times the integral over the function. Right? C is a constant value, so it can be pulled outside of this integral. There's something very similar to the addition and multiplication or addition subtraction rule for integrals as well. And then here is an important property right here. So this shows that there are actually two different kinds of versions of integrals. There is indefinite integrals, which would be this version here, and there are instead of indefinite integrals, there are definite integrals, which is this version here. And a indefinite integral is just generic trying to find something that is the antiderivative. And it has a kind of indefinite nature to it that we'll talk about. This version here, where I'm talking about a definite integral, this is the area under a curve between 2 points, right? Point A and point B. So this, since you've specified the region under which you want to find the area, has no indefinite nature to it at all. It is perfectly definite. There is a starting point and an ending point, and you are going to take the area underneath the curve between those 2 points. Now, the most important rule that you're going to need to know for this class is this one right here. Okay, it is the opposite of the power rule. Okay, so earlier we had said that if you have some function, f of x, that is ax to the n plus bx to the m, then you can get the derivative by doing the power rule, right, where you multiply the exponents out front, and then you drop the exponent by 1, right? And I like to put it in this form because it includes the constant multiple rule and the addition rule right in there. Now, let's talk about going in the opposite direction. Well, let's say that you wanted to have some function, capital F of x, such that when you take its derivative, it will be equal to this ax to the n plus bx to the m. Well, since you know how the power rule works, you know a bit about what this function should look like. So you know that once we take the derivative of this function, it should have a form like ax to the n plus bx to the m. So let's find a function that once we take its derivative will look like this. Well, because of the constant multiple rule, we know that those constants won't really change. So we're going to have both of those constants plus something. And we also know, because of the power rule, that we're going to have something with an exponent that's greater than x to the n, right? Greater than x to the m by 1, so that once we take the derivative, it'll have this x to the n and this x to the m. So there's going to be some x to the n plus 1 in here, some x to the m plus 1 over there. And also, once we take this derivative, we know that this x to the n plus 1 will be multiplied out front, and then it'll be dropped down to the value that we want down here. So if it's going to be multiplied out front, we should probably divide by it to begin with so that it won't mess up our coefficient. Okay, now this is the antiderivative of this function here. Okay, let's just try it. We'll try it on for size. So if I take the derivative of this thing here, right, because of the constant multiple rule, that a stays the same. The derivative of x to the n plus 1 over n plus 1, well, I'm going to drop the coefficient out front and drop its power by 1. Well, when I drop it out front, it gets canceled by that n plus 1. And dropping the power by 1, it's just a x to the n. And the same thing happens for the next one. The constant stays there. X to the m plus 1, the derivative of that is going to be m plus 1 x to the m, right? Because the exponent drops by 1. That the m plus 1 will show up then in the numerator and in the denominator. The two things will cancel out so that I have x to the m. So you can see, right, once I took the derivative of that thing, it was exactly the desired quantity. Okay, now there is one part that is missing to this. You might have noticed this, but since the derivative of some constant value is equal to 0, I can also add a constant value onto this. And when I add that constant value, because of the addition rule, I can just take the derivative that I had already found and add the derivative of that constant, right? But the derivative of a constant is 0. So I get the same exact thing when I add on any constant value. So that's interesting. This is what brings out the indefinite nature of some integrals. If what you're looking for is just some function such that once you take its derivative, you get your desired, in this case, polynomial, then adding a constant value to that function will not change your desired outcome at all. So there is this kind of inherent arbitrary overall level that you have to take into account. So let's take a look then back at my original example, right, where I had f of x is 8 plus 8x minus 3x to the third. Now, I want the antiderivative of this thing now. Here's how I would write it. Okay, capital F of x is the integral over f of x dx. Okay, in the same way that derivatives are always done with respect to some value or some variable, whether it's x or t or y or whatever. The same thing happens with integrals. You're always integrating over some variable. Here I just plugged in the value for f of x. Now I can apply the antiderivative power rule for each one of the individual terms, right? 8 times, so here you have a constant multiple, 8 times 1 is a good way to think about it. So in this terms where x to the n becomes x to the n plus 1 over n plus 1, right? If n is 0, which is the case where we have with 1, right? For 1 is where n equals 0. The antiderivative of that term, when you plug in 0 in here, is x to the 1 over 1, right? So the antiderivative of 1 dx is just x. So that's where this comes from. Now we have plus 8 times that antiderivative of x, right, which would be increase the power by 1 and put that same thing in the denominator, so x squared over 2, minus 3 times the antiderivative of x to the third. So that would be x to the fourth over 4. And then I have to add on my arbitrary constant there. So c, whenever you see me write down this plus c, unless otherwise stated, I'm using an arbitrary constant. Sometimes the conditions of a problem will tell you what value that c must be. But right now I'm just talking about a generic antiderivative. I'm looking for the class of functions such that when you take its derivative, you get my desired original polynomial 8 plus 8x minus 3x to the third. So that would be, this class of functions here, where c can be any constant value, right? Note that c cannot depend on x, right? It cannot have any x dependence, but it can be any value. It could be pi, it could be e, it could be I, an imaginary number. Either way, that value will go away once I take the derivative. So this here is my capital F, or my antiderivative of my function. Now let's take a look at definite integrals. So a definite integral is when you're interested in precisely the area between two specific points. Okay, and when we're talking about the definite integral, we put these definite limits, the 2 points under which we're interested in the area of the curve, up here and down, down here for the lower limit and up here for the upper limit. So this says, give me the integral over this function f of x dx from x equals 0 to x equals 2. It's telling me find this area right here. I want it to start at x equals 0. I want it to end at x equals 2. So I chose a convenient location since the curve reaches 0 at x equals 2. So there I'm just saying, give me this exact area here. And this is contrary to the indefinite integral where I was saying, give me whatever function you need whatever function will give me something that when I take its derivative, it gives me back my original f. Okay. So hopefully you can see how this has a definite value. There is one and only one area underneath this curve between these 2 points right here. Okay. Now, so here I'm just plugging in the value for what f of x was. Here I wanted to show that there are 2 different ways of writing this. So the more explicit way is to write, from x equals 0 to x equals 2. Sometimes you see, just for short, just a 0 and a 2 there as the lower limit and the upper limit. Okay. So the way that we write this, this is all important notation for you to understand, right? So the antiderivative of this function here was capital F, which we had already found. And when you take the definite integral, you're going to take this antiderivative, this thing that you found there, and you're going to evaluate it at x equals 2 and at x equals 0. And you're going to subtract the 2. So you're going to take the antiderivative at the upper limit minus the antiderivative at the lower limit. Okay, and this will give you the area underneath the curve. So let's do that. So this was the antiderivative that I stuck in over here, right? I dropped the constant. The reason why is because when I take these two, when I take this difference between capital F at those 2 points, right, the arbitrary constant has to be the exact same here as it does over here. So it ends up canceling out. Okay, so I can just take this thing without the constant and put that in for f of capital X over here. Then I'm going to evaluate it at the top of the region minus its value at the bottom of the region. Okay, that's what this notation here means. Okay, sometimes you see it as a vertical bar. Sometimes you see it as, so sometimes you'll see it like this. Sometimes you'll see it like I'm writing it here as like a bracket. Sometimes you'll see it as closed brackets, f of x, 0 to 2. These are all just notation things. What it means is, in every single case, take 2, plug it into the function here, subtract the function evaluated at x equals 0 from that value. Okay, so whatever form you see this in, it all means the same thing. Take f at the top of the range and then minus f at the bottom of the range. So when I do that, when I take these in here and I plug in x equals 2 there and x equals 0 there, right, you'll notice that the 2 c's are going to cancel out, right? Plus c there, there's a minus in front here, so that those 2 things cancel out there. And what I get is 20. So after plugging in all of those values. So the definite integral gives me a definite number, right? So long as there's no variables up here at the limits, right? I can take a definite integral, as I do here when I'm making my plot, from, say, some definite value, 0, up to some function, some variable x, okay? And when I do that, then I'm not going to get a number, right? I'm going to get out a function, right? A function of x. So here I've plotted then my integral of f of x from x equals 0 to x equals x. So you can see, right, once I get up to x from 0, say, so that when the upper limit of my region here is 2, as it was over here, right, then I can go over what is the value at x equals 2? Well, it's 20. Okay, so the two things agree. So this curve tells me the area of the curve from 0 up until whatever x is. So obviously, when x is 0, then there's no area underneath the curve. But the thing will continuously rise. It reaches its maximum point at x equals 2, right? That's this area here. Then, after I get past the point where x equals 2, I'm now into a region of negative area here. So the capital F of x, the integral of f of x from x equals 0 up to that point where x is greater than 2 starts to drop a little bit because that negative area is going to bring this thing down.